All right, hey everyone. It's day 19 of Advocate of Code 2015. Oops, let me update my little sticky here. Day 19. All right, let's see what our puzzle is today. Day 19, medicine for Rudolph. Rudolph the red-nosed reindeer is sick. His nose isn't shining very brightly and he needs medicine. Red-nosed reindeer biology isn't similar to regular reindeer biology. Rudolph is going to need custom-made medicine. Unfortunately, red-nosed reindeer chemistry isn't similar to regular reindeer chemistry either. Okay. The North Pole is equipped with a red-nosed reindeer nuclear fusion fission plant capable of constructing any red-nosed reindeer molecule you need. It works by starting with the same input molecule as some input molecule, then doing a series of replacements once per step until it has the right molecule. Okay, this sounds familiar. However, the machine has has to be calibrated before it can be used. Calibration involves determining the number of molecules that can be generated in one step from a given starting point. For example, imagine a simpler machine that supports only the following replacements: H to HO, H to OH, O to HH. Given the replacements above and starting with HOH, the following molecules could be generated. Oh shit. I'm already scared. HOOH via HHO, the first H. HOHO via H to HO on the second H. Okay. Then we have OHOH via H to OH on the first H. HOOH via H to OH on the second H. HHH via O to HH. Okay. So in this example, there are 4 distinct molecules, not 5, because HOOH appears twice, after one replacement from HOH. Santa's favorite molecule, HOHOHO, ho ho ho, can become 7 distinct molecules over 9 replacements, 6 from H and 3 from O. This machine replaces without regard for the surrounding characters. For example, given the string H2O, the transition H to OO would result in OO to O. Your puzzle input describes all the possible replacements and, at the bottom, the medicine molecule for which you will need to calibrate the machine. How many distinct molecules can be created after all the different ways you can do one replacement on the medicine molecule? How many distinct molecules can be created after all the different ways you can do one replacement? Okay, so I only have to do one replacement. I don't have to do it recursively yet. I have a feeling I'm going to have to do it recursively. I'm going to have to do one replacement, and then I'm going to take all of those replacements and run it again. So that's going to be a high-performance molecule. Okay, so let's get the puzzle input. Let's see what it looks like. Oh, damn it. Look at this crap. This is what we start with. These are all the rules. God damn. Okay, what the shit is this? H to C blah 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 blah? Oh my god, look at all these H replacements. Oh, damn. Okay, okay, let me take a look at the puzzle. Oops, that's the wrong puzzle. Let's close that. Let's go back to the puzzle input. Okay, so it looks like we have a whole bunch of rules, and then one empty line, and then what appears to be the actual molecule on the last line. Okay, so I'm going to do this. I'm going to create a test case that sort of mimics that same format. Text. Okay. And the rules are going to be here. These are the rules. There's one empty line, and then the molecule is HOH. Okay. And the expected output is going to be 4, because there are 4 possible molecules that can be made from this molecule using after one step. Okay, so how am I going to solve this? Let's bring back QuickTime. Let's see if I can sketch something out. So we have our long okay, so the first thing we should do is probably parse out our rules. So a rule is going to have let's see here. It's going to have an input, and it's going to have an output. And there are going to be multiple rules that have to use the same input. So we have multiple, like in this example, we have 2 ones that would do H, and then each of them has a different output. So in that case, we'll probably have to go through this. So then for each input, oh shoot. Do we have to do each unique input? No. each individual input. So we have our start molecule, and from the start molecule, we have a list of different rules. So we have rule 1, rule 2, rule 3, right? And then from each rule is going to produce a different output molecule. So it's going to be out 1, out 2, out 3. But the input is always going to be the same. You don't have to do any recursive. I have a feeling part 2 is going to have to say, oh, and then for each output, run it again, and then it's going to fan out, and it's going to be a nightmare. So let's see. So for each rule, so the molecule is probably going to have duplicates. So in the case of this one, we have HOH. The word letter H appears twice. So for each one of these rules, we have to find, for each rule, it's going to have to be multiple passes for each occurrence. For each occurrence, right? So in the case of HOH, let's erase that. In the case of HOH, let's actually just, go ahead and do a little test case here and draw it out. So we have HOH. So then rule 1 is, so the first rule is the H, and it goes to HO. So that means, and there are 2 H's, so that's going to have H to HO is going to have, this needs to be run for each individual H. So you have 1, 2. So we have HO, OH, and then H4, okay, and the second one is going to be HO, HO. I do have a second test case here, I just realized. Okay, so then the second one is going to be, we still have H, and we have H to, we have H to OH. Is that right? Yeah, H to OH. And that is going to be OH, 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 or HOOH. So once I have all of my outputs, all I have to do is dump them all into a set, and that'll remove the duplicates. And then I can count how many are left in the set. And then the last one, so there's only one O. So that one, O to HH, right? Actually, I only need to do one arrow because there's only one H, right? So we get 2 of these arrows. We get 1 arrow for each occurrence of the letter in the input, and then 1 arrow, and then, so we get, I guess that makes sense. Okay, good. So I think that gives me something to start with. I'm going to go ahead and parse the input. All right, so the first step is to parse. I'm going to write a function called parse input. And it's going to take the input, and it is going to return a tuple, and the first tuple is going to be an array of rules, and the second tuple is going to be a string, which is the molecule. Okay, and now I need to create a rule, struct rule. So a rule is going to have an input, input, and that's going to be a string, and it's also going to have an output that is also going to be a string. And so init descriptor. So for the descriptor is going to be this, right? It's going to be 1 line. So we're going to have to split it. Actually, do you know what, better yet? I'm going to use a regular expression. So open a debugX. I could probably just write it from memory because it's not complicated. So if we have our H to OH, H to HO, I mean, we're going to do open parenthesis, close parentheses. It's going to be \W plus, and then space, and then we do another one, \W plus. There we go. Group 1, group 2. Boop. Let groups equals regex parse descriptor. I need to double escape these backslashes. Oops. Okay. Now self dot input equals input. No, groups 0. I'm going to go ahead and unwrap that because groups is going to be optional. Self.output groups 1. Okay, so that's our rule. Yeah, missing return function. Okay, and then we need, so this thing, we have range. Okay, so here's what I'm going to do. Lines, let line groups equals input.lines.split an empty string. I think that should work because there's going to be one line that is an empty string. And then we're going to do let rules equals line groups 0 dot map. Oh, that's already a string. Line groups dot 0 dot map rule dot init. And we're going to do let molecule equals line groups 1 first. There should only be one element in that. Return rules molecule. Okay, good. So now all I have to do is say let rules molecule equals parse input. Okay, so now we have our rules, we have our molecule. So now for each rule, we need to, let's do a reactor. Let's create a class called a reactor. And we're going to have a var start molecule. That's going to be a string. And we're going to have a, should be a reactor because it's going to create reactions. Okay, let's start molecule. It shouldn't change. And then we also have let, should I have a, I have an idea. So we're going to do init, start molecule, string, self.start molecule. And function, I'm going to say function is going to do react with rule. React with rule. It's going to have an output string. No, it's going to have a set of strings, right? Because there might be more than one occurrence of the start molecule. So by reacting with the rule, we're going to have a set of strings. So we're going to have var set results reactions equals set string. We're going to initialize it to an empty set, and we're going to add reactions to that as we compute them. So then now we need to know the location of every start molecule. So given the input, we need to do, should we do a regular expression for this, or should we do a find and replace? I wonder if I can, I want to get the index of every beginning of the letter. So if we have our test case, so if we have HOH, I want a function that will take this input and give me index 0 and index 2 for the two H's, right? So for the input is H, give me index 1, index 0, index 2, and then probably a range, because some of these in the final puzzle, in the actual puzzle input, are multiple characters. Like we have AL, CA, MG, SI, TH, TI. I think everything is, it's chemistry, so it's going to be, a normal element naming convention, so it's uppercase then lowercase. But nevertheless, I want to be able to find every index. Let's just see if there's a function called all indexes of. So we have start molecule, all indexes where? Is there index where? No, I have first index, form index, no, last index, first index. Geez, this is first index where? First index of, and this could be first index of a character. Where? Okay, so how are we going to do this? We need to... All All right, let's try something else. Let's go back to I might be able to use regular expressions for this. I might be able to do like a kind of a tricky regular expression. So we have HOH. And if I want either an H or an EW. No, that's not. I want to be able to capture the group. H or anything. Okay, all I do start molecule dot substrings. Enumerate substrings. Enumerates the substrings of the specified range of the string. In range expression. Shoot. I might just have to do it manually. I might have to scan through the entire yeah, here's what I'm gonna do. I'm gonna create a function. I'm gonna say occurrences of element string, and this is gonna return a set. Maybe I'll just do an array. It doesn't really matter. I'm going to do an array because in order for sets to work, the value has to be hashable, and rules aren't necessary. I mean, they could be hashable, but I'm not going to bother. So, okay, so we have our start. No, what is it going to return? It's going to return an array of each index and range, right? It's going to return an array of index and range. So it's going to be string.index and a range, string.range. Is that a thing, or do I have to do NSRange? Let's do NSRange. Okay. Oh, no. String dot range. No, NSRange. Okay. So for this, we're going to enumerate through the entire string. So we have our start molecule, and we're going to do do we have to enumerate? We have to enumerate, don't we? We have to do enumerated. And then for each filter? No. No. Is this index and element? I think I might have this backwards. This is return true. Error type. Cannot convert value of type to closure type bool. What are you talking about? Okay, I'm getting lost here. I'm gonna return an empty array for now because I want this to compile, because I want to make sure that I got this right, that it is indeed index first. Cannot convert value of type to closure result type bool. I just read return true and you yelled at me. True. Because filter is a return true. I mean, it's a return Boolean closure. T was never used. Okay. Okay, that's the integer. And that's the character. Okay. I'm going to call this char. I'm going to call this index. Okay. So given the... oh, wait a second. No, I'm going to do map. I'm going to map it first, because what I want is I want an array of string index and then NS range. So the element that needs to, it's going to have a character length. So we're going to say, we're going to do let length equals element dot characters dot count. And we're going to do, so for the index, we're going to look at the current index and the index to the right. And the number of the length, so if the length is 2, we need to collect 2 characters. We need to collect the character of the current index and the one ahead of it. So that's going to be guard let if length, I mean, there's only one or two, right? Okay, let's do this. If length equals 1, that'll be very simple. We just need to return char at the NS range of index dot is it going to let me do an index? Because no, that is an index. No, wait, what? That is an integer, right? What is going on? Why am I getting this weird cursor? Here. God damn it, Xcode. Okay, I'm holding the Option key, and it's like I want to be able to select this index. Unable to infer complex return type. Okay, so that's just going to return. Here we go. String.index NS range. No. It's going to be length. This isn't going to be an NS range. It's going to be an integer, right? Because it's going to be the length of the integer. Right, so the string.index is actually the index of the string, and the integer is the length of the scan, right? So that's going to be the stuff that we replace. Okay, so length equals 1, 1. Ooh. Is this even valuable? Return index length. Type of expression is ambiguous without more context. Let ranges. And then if and then ranges return ranges dot filter self dot element, and this is going to be a index and a length, and we're going to say let start index equals index, let end index equals index dot advanced by length. How is this ambiguous? Okay, index, int. Equals element. No. Start molecule dot start index advanced by index string is no member advanced. string.index. No, it's offset by, isn't it? No, it's dot index after, no, index, start molecule, start index, offset by length. No, offset by index. Man, I hate doing substring operations in Swift. It's such a pain. You have to do all this index crap. Okay, start index advanced. No, this would be shit. Okay, so we have to do start molecule dot index, start index, offset by length. There we go. And then if, this should be, so if end index is start molecule dot and end index is greater than or equal to, no, is less than or equal to end index. So if end index is past the end, then it's no good. We need to return false. Otherwise, we're going to return a string. No, otherwise let string equals index dot I thought I had whatever. I thought I had a function that could like scan through a string and then get the pairs, but maybe not. Okay, string equals index dot, no, string equals start molecule, start index dot less than. I guess it would be like that. Dot end index, right? And start index dot end index. So then we're going to do if return string equals element. I mean, I guess. Okay, so then we have let occurrences of, no, let occurrences, I'll let occurrences equals occurrences of rule.input, right? Okay, that's good. So we have our occurrences of the input. So this will give us an array of elements that match the rules input. So the first value should be the index of the start point of that element, and then the second value should be the length of the element. It's either going to be 1 or 2. So then given our occurrences, and this is only the ones that are valid. So given these occurrences, we're going to replace, so we have our var molecule copy equals ns string of start molecule. Is that going to be allowed? Can I initialize ns string with a Swift string? Missing, okay. Okay, so then we have molecule copy is going to be an ns string. Now the reason we have to do an ns string is because ns string has actually some functions that are missing from the Swift, I shouldn't say missing, but ns string has some helper functions that do not exist in the Swift string implementation. In particular, replacing strings at ranges. So we have molecule copy dot replacing occurrences, replacing characters in ns range. Aha. So we're going to do, okay, so it's what I want, occurrences dot map, and is going to be replacements. And we have our, what is this? Index, start index length. And we're going to do molecule copy, replace. We're going to do, here we go, return molecule copy, replacing characters in ns range. index length with rule.output. There we go. Okay, I think that does it. And then we just have to return a set of replacements. Oh, and this has to actually initialize start molecule. That has to initialize to something. Okay. What now? Unable to infer complex return closure type. Molecule copy, replacing characters. This should return in a string. Am I wrong? Okay, cannot convert. What is this? Expression of type string to return type NS string. Oh. Well, that actually works in my favor because I want it to be a string anyway. Missing argument. Location length. Oh. Location length. Okay, reactions never used. Oh, I don't, yeah, because I don't actually need this. And this is not changing, it's not mutating, so I can make it a let. It's a constant. Okay, how are we doing? Am I getting any other warnings? Okay, build succeeded. No warnings. Oh, well, I do have warnings up there, but nothing in my actual reaction, my reactor here. Okay, so we have our rules. We have our starting molecule. So now for each rule, we want to let all reactions. So for each rule, we want to, no, we actually want to create a reactor. Let reactor equals reactor, and start molecule is the molecule. And then with the reactor, for each rule, rules.map, actually want to do a flat map, right? Because we want to bring them all together. And we're going to have a rule. Oops. And we're going to have a reactor.react with rule, right? And that should, see, because this is probably going to expect an array as return value. Oh, maybe not. Let unique all, say all reactions. Okay. And then is this going to be an array? It's going to be an array. So I do want to I want to convert it into a set. Let unique reactions equals set all reactions. And we want to return the count of unique reactions. Okay, I really hope this works because I got kind of lost when we were building this occurrences function. So let's hope for the best. Let's cross our fingers and hope for the best. Let's compile this one more time. And while that's compiling, I am going to get my second test case out. So it's going to be exactly the same as the first test case. The rules are the same anyway, but it's going to have a different different molecule. Right? Ho, ho, ho. Can become 7. Six from 6 and 3 from O. Over 9 replacements. Okay. All right. Let's clear. Let's do, oops, PB paste, pipe to Swift run, advent, Swift run 2015 _ 819, right? Oh. Advent of code. Wait a second. I don't know if I think I forgot to copy my, here, I got to copy the puzzle input to my clipboard here before I do this. Ooh, test cases failed. Not attempting to solve. Okay, interesting. Why did our test cases fail? 0. Now, why did I get 0? Did I forget to return the, no, okay. Let's see how many occurrences. There might be something wrong with my occurrences function. Print occurrences for rule.input. And it's going to be occurrences. Yeah, okay, so that's an empty array. So something is wrong there. So let's see. So ranges, start molecule, enumerated, da, 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 da. I'm going to print ranges. Print element. Print element. Print ranges. Okay, so we have HHO. Okay, that's good. 0, 1, 1, 1, 2, 1. Okay, so the length is fine. So then occurrences for H, 0, 1, 1, 1, 2, 1. Occurrences for H are 0. So the ranges are correct. The problem is that it is not finding the... It says that this is not an H, is what it's telling me. So starting at index length 1, it says this is not an H, which is not true. It definitely is an H. So there must be something wrong with... I'm going to just... I feel like I just want to declare bankruptcy on this function right here. And instead I'm going to do let range equals ns range index. Actually, better yet, I'm going to do... Here's what I'm going to do. I'm going to take this function here. And I'm going to return... This is we're going to return an ns range. I'm going to do all this nonsense. This little tuple here, it's just an ns range. That's all it is. I'm just going to call it what it is and make it an ns range. Ns range... Location, index, length, good. Now we have our ranges. Now this thing we don't even need anymore because this is going to be a range. In range. Okay, oops. Let's build. Okay, and this is going to say, oh, you only have one thing here and you put 2. How foolish you are. Okay, so we have let substring equals element, no, start molecule as ns string dot substring with range, range, and then return substring equals element, right? This might actually have a fatal error because we're trying to get the substring. So like, for instance, this one here, index 2, length 1, that's going to go past the end. Yep. So maybe we should start by filtering out anything that is not, that's past, well, okay. If guard start molecule dot range, is there get bytes, range of characters, line range, paragraph range, compare, remove subrange, replace subrange, replacing occurrences of options, blah, blah, blah. Contains range. Contains where, contains element. Nope. Start molecule dot characters dot count. Let's just do this. Is greater than range plus location plus range dot length, right? So there has to be more characters in the string than the length plus the oops, that should be location. So in the case of, ooh, what happened here? What the heck? Oh, it's because my test case is passed and now it's trying to chunk. Oh, ooh. Huh? Hold up. Starting at length 505. Greater than or equal? Okay, let's try that. Else return false. Okay, this is interesting. So it seems to be running. I'm going to go ahead and delete these print statements. Okay, I'm not printing anything else. Okay, this is still going. We're on H now. Okay, there's probably going to be a few of these. MG. Okay, N. Now we're on N. Now we're on O. Now we're on P. SI. TH. TI. There's an opportunity for caching here. Occurrences for E. There's no lowercase e in my entire formula? Huh. How can that be? Oh, I wonder if that's going to be a recursion. Really? Lowercase e. That's it. There's only and they're all inputs. Maybe that's part of part 2. Okay, the answer is 535. Let's see if that is the correct answer. Come on. Yes! That is the right answer. We are 1 gold star closer to the powering the weather machine. Okay, so that was actually pretty slow. We had an opportunity for caching there. I think we do not need to do this occurrences of element more than once per input, but let's see what part 2 brings us. It might not be a big deal. Now that the machine is calibrated, you're ready to begin molecule fabrication. That was only calibration. Damn. Okay, this might be a while. Molecule fabrication always begins with just a single electron, E, and applying replacements one at a time, just like the ones during calibration. Okay, so this is that mysterious letter E that we saw in our puzzle input. Now that's becoming part of the solution. Okay. For example, suppose you have the following replacements. E equals H, E equals O, H blah blah blah. If you'd like to make HOH, you start with E, and then make the following replacements. E to O to get O, O to HH to get the HH, and then H to OH to get the second H to get HOH. Oh, so you could make HOH after 3 steps. Santa's favorite molecule, ho ho ho, can be made in 6 steps. How long will it take you to make the medicine, given the available replacements and the medicine molecule in your puzzle input? What is the fewest number of steps to go from E to the medicine molecule? Oh my god. I don't even know where to begin. What the hell? Do I need to go back? I need to go backwards. I need to boil the molecule down into an E, into a single E. Oh, shit. Okay, so now I need to go in reverse. That's what is happening. Oh my god. I need to keep reversing it until I'm left with a letter E. Steps go from E to the medicine molecule. How am I going to do this? All right, we're going to bring the tablet back. So I'm wondering, so given our output, so in this test case, so we have, I mean, they're doing it forward, but we're going to have to work backwards, I think. We're going to have to start with HOH and then do backwards replacements to go from HOH, then to get the HH, then to get the O, then to get the E. Interestingly, okay, so this is interesting. So given HH, another solution would be to go from HH to E, to E to E, right? Oh, no, but then I have two E's. And you can't have two E's. The E has to be the last step. The thing that makes me nervous is, like there's a risk for like infinite recursion. I mean, look at this one, B to BCA. I mean, you could infinitely go B to BCA, CA, 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 CA with enough steps. Solve this. I'm like racking my brain right now. Okay, so I guess we have to start with something, right? So let's assume, all right, so let's assume that we have our HOH, and then we want to work backwards. So we have our rules. I'm going to go ahead and erase this. Oops. You know what? I'm just going to go ahead and erase all of this. Da-da-da-da-da. So starting with HOH, we want to look at our rules and we want to see which rule will reduce it the most. I think that's probably going to be our strategy for success here. We look at all of our rules and we say, okay, so we have rules such as E to H, E to H. We have E to O. We have E to, no, we have, and then we have the old rules, which are H to HO. And we have H to OH. And we have O to HH. Right? So given this puzzle input, I need to find the first, looking through here, the first thing I would do is I would say, okay, so we have H to OH. So let's see here. So OH is probably the first thing that would be boiled off. So, or no, we have HO. We also have HO. So I would go, do we have an H? So we're going to sort this by the length of the output. So that we have HO, OH, and HH, and we want to make it smaller. So we have H to HO. So HO is going to be, so we're going to replace HO with, so if you take this, that'll be HH. And then this is also HH, right? And that doesn't fit. Okay. And then from there, the next longest one is this. So then we have O. And then from there, we have E. So that's what? 1, 2, 3. Okay. HO can be made in 6 steps. Okay, so now let's try Santa's HO. Let's try ho ho ho. Let's see if we can get arrive at the same answer. So we have ho, ho, ho. So looking at this, so we have H to HO. So if we do that, we would have H, HO, HO. That's one. Or we would have H to OH. Oh, shit, see? Now we have another one of these problems where it's going to fan out. So it makes H, HO, HO, or it makes ho, HH, ho, H ho, or makes ho, ho, H, right? It makes one of those three. Okay, maybe that's how we have to do it. We have to, for each step, we're going to come up with a set of steps that are possible from the next one. Got it. Okay, so this is going to be step one. So now we have our set of steps, our set of step ones, possible step ones. Then for each one of those, now we're going to go on to step two. So for each step one, we want to see what are the possible outputs for step two. And then for each step two, we need to know what are the possible outputs for step three, and so on. So this will probably take a very long time, but I think we can do it. So then, okay. Okay. Func, reverse reaction, reverse react with rule. That's going to return a set of string. So it's going to be basically doing the same thing. We're going to get our occurrences, and we're going to get rule.output. Right? So we're going to get our occurrences of the output, and then we're going to do a replacements, occurrences map, range string, molecule copy on a string, start molecule, placing characters in range with output with input. We're going to reverse it. And then we have this set of replacements. So, it's a reverse react. We're going to say func boil molecule down, do steps to reduce molecule. So we're working backwards. Now the puzzle description is basically we're starting with E and then we're working forwards to the medicine molecule. But in order to solve this in a reasonable amount of time, we have to work backwards, I think. Oh, interesting. But maybe we can work forwards. I mean, we could apply the same principles and work forwards rather than backwards, but we would be working recursively. So we start with an E, and then we keep replacing it until we find the target molecule. So I don't actually have to I was approaching that as reduction, but we could actually do it forwards. Let's keep going down this path, and yeah, I guess let's keep going down this path, see what happens. Steps to reduce molecule, and it's going to return an integer. And we have our start. Okay. Oh. Molecule input molecule string. It's going to be optional because if I'm going to say string equals nil, and if it is nil, we're going to say let start equals molecule or start molecule. Okay, so we're going to default to the start molecule if that is not passed. So given this, we're going to say let say minimum steps. Minimum steps to reduce molecule. We're going to say all unique molecules equals start reverse. Oh no. using rules. Rules would probably be an instance variable. That's okay. Unique molecules reverse react with. No. Unique molecules equals a set, and we're going to start with the rules, map and rule, and we're going to say reverse react. Oh no, you know what? You know what? I'm gonna can this. I think the right thing to do is start with the E. Just follow the puzzle instructions. Instead of trying to overthink it, I'm going to follow the puzzle instructions, start with the letter E, and then run recursively until I reach the target molecule. Func. Minimum steps to reach target molecule. Integer. Minimum steps to reach. Should be reach, not react. Reach. So you start with E. So we're going to, okay, so basically need to go back to puzzle 1. Let reactor, all reactions. Here we go, unique reactions. So we have all reactions, we have rules using rules. Okay, all reactions, rules.flatmap. Return react with. And then unique reactions, set all reactions. If unique reactions I need to have another argument here because I need to run recursively. Iteration equals 0. If unique reactions dot contains target molecule, we're going to return iteration plus 1. Otherwise, we're going to return the minimum 1 plus minimum steps to reach target molecule. Min. Oh, shoot. So the thing that I'm worried now is I'm going to be going down a lot of long dead ends, I'm afraid. Oh, shoot. This is not a good approach. Okay, maybe I just need a new class. that's what I'm going to do. I'm going to create a new class. I'm going to create a class, and it's going to be called Molecule Builder. And the Molecule Builder is going to have a start molecule. It's always going to start with E. It's going to have a target molecule, and that's going to be a string. And it's going to have rules, and those are going to be like that. And the Molecule Builder is going to have this function. And so in order to build the molecule, we need to start with a reaction. Minimum target. Okay, so func minimum steps to reach minimum steps from starting molecule. Part of the problem is that I want to, once I arrive at the target molecule, I want to stop. I don't want to have to I don't want to have like these stray branches, going off into infinity, trying to compute all these different possible permutations of molecules that are completely relevant to our puzzle. So, man, I am just at a loss here. So how am I gonna do this? I guess we just got to do it one step at a time, right? Starting molecule. We're gonna do iteration. Iteration equals 0. Maybe that should start at 1. Let's start that at 1. No, iteration. We're gonna start at 0. That's gonna be the one we're starting at. So then we have our starting molecule. So is let reactor equals possible next molecules equals starting molecule dot equals reactor start molecule starting molecule. And then dot do let reactor dot react with puzzle input. Okay, so here's what I want to do. I want to take all reactions. I want to take this formula here, and I want to build it into my reactor. So we're going to do let react with rules, plural. Okay, so given our rules, with rules.flatMap, connect with rule, unique rules, reactions, and we're going to return unique reactions. Okay. Whew. With rules, let next steps, and then if next steps contains the target molecule, if next steps that contains target molecule, and we return iteration +1 because we actually needed to do one more step. Otherwise, maybe this should just have a private variable for iteration. Private var iteration equals 0. And then we can remove that. See, so instead of doing a recursive function, I will just scan over func. We're going to do private var available reactions. Possible outcomes at current step. And that's going to be replaced every time we iterate. Possible outcomes at current step. And we're going to have a function, func, completes is completed. That's going to return a bool. And then return possible outcomes at current step dot contains target molecule. Okay. And we're going to do, instead of minimum steps, we're going to do func next step. Oh, shoot. Okay, so func next step. Okay, we're going to do all our next outcomes. Outcomes equals set string. And we're going to create a reactor. Then we're going to do possible outcomes at current step. This is going to be E, the letter E. But I need to wrap it in an array. Possible outcomes at current step dot map, flat map. Possible outcomes at current step molecule, and then we're going to next steps, return next steps. Oh, this would be a func. Duh. Please use compact map for the case where an optional returns an optional value. This is not an optional. This should return a set of strings. Cannot convert set string. I don't want it to be an optional. What is going on? Do I have to do it as an array? Okay. I don't understand what's going on here. That should be allowed. Is it not? There, okay. Initialization of next outcomes is not, okay. Let's do that. Next outcomes. It's an array of strings. I'm gonna make this a set. And then we're going to do, we're gonna do iteration plus equals, oh, here we're gonna put that up here. Iteration plus equals 1. Next outcomes. And actually, let's just do this. Let's do possible outcomes at current step. And we're going to process them. And then, okay, and then we're going to, has no initializers. Oh, okay. That's fine. So then we're going to do func run. And this is going to create a loop while true. No, while is not completed. Right? And while it's not completed, we're going to do next step. We're just going to keep running steps until it is completed, and then we're going to be done. So now we need initializer. I think this was actually quite an elegant solution after all of that thinking and pondering. I think we've arrived at a pretty good solution. Okay, so target is a string, and rules is an array of rules. Self.target molecule equals target. Self.rules equals rules. Okay, so now let's go to our puzzle. Ooh, what's happening here? Can I find reactor? Oh, that's right. This has got to be a self. Unique reactions set of... Oh, okay. So we're going to return set like this. Let's just do that. Okay, so now our test cases. Okay. 3. You have 3 steps for that, and then Santa's favorite molecule, ho ho ho. We have 6 steps. HO, HO. You can get there in 6. Okay. All right. I mean, I think this is going to be possible outcomes at current step. I think, geez, I hope this works. All right. We have our rules, and we need our let builder equals molecule builder. Target is the molecule, rules is the rules. And we're going to return builder dot. Oh, this needs not to be private. Dot iteration. Okay, we're going to do builder.run. So this is actually good because as soon as it finds a step where the correct molecule is created, it'll shut down and stop, and it won't do any more steps. So I don't have these runaway branches where something is going to be recursing infinitely. Okay, so I'm going to go ahead and I'm going to return unsolved for that because I don't want to run that again. I think it's going to be too slow. And so with that going, let's code after return. Okay, yeah, that's okay. Test cases failed, not attempting to solve. Running test cases on B. Uh-oh. I thought it'd be faster than this. Oh, of course. I know why. Because I forgot my little, I forgot my E rules. Duh. It's just running infinitely on, it's just in an infinite loop because it's not actually, it's not replacing that E. Post just E every time. All right, let's try again. Oh, boom. That was quick. All right. Let's see how this plays out. This might take a long time. Because I'm doing the reactions so much more frequently now, I might actually benefit from caching that occurrences function, because I think that I have a feeling that's probably where the bulk of the work is going. All right, I'm going to see if I can make this a little bit so it's not bumping into my video here. Okay. So while that runs, I'm going to see if I can race it. And if I come up with a caching solution, then I'm going to go ahead and stop this and rerun it, because I think the caching will help it. move much more quickly. So with our reactor, we have our occurrences of element. We want a cached occurrences. It's going to be string and an NS range, an array of NS range. So first thing we want to do in this case, let's do equals. We're going to guard. No, we're going to do if let cached ranges equals cached occurrences at element, return cached ranges. And then at the end, we need to actually set the cached occurrences. So we're going to do let ranges, let valid ranges equals, and we're going to do cached occurrences at element equals valid ranges. That should do it, right? All right, I'm going to go ahead and kill this. I'm going to run it again. Hopefully I do faster than 4 and 11 this time around with my caching solution. Uh-oh. Oh, because it didn't actually return valid ranges. Okay, it's a little bit faster. Granted, the impact might be much more impressive on the actual puzzle input because it's much bigger, obviously. Running step and iteration +1. Okay, yikes. We're on step 6 and it's already choking. What can I do to speed this up, I wonder? I mean, at this rate, it's probably going to take an hour. There's no way. It's got to be like, 100 steps or something like that. I'm trying to think of how I could make this any faster. Like, are there any shortcuts I could take? Because, you know, these should be solvable. Like, the program should run in, like, less than 15 seconds. And I'm sitting here, you know, I don't know how long this has been running so far, but it feels like we've been sitting on step 7 for quite a while. God, we are still on running step 7. What is going on? I mean, is it really just expanding that quickly? 607 possibilities. 3,566 possibilities. What if I had... Oh my god, 21,287 possibilities. What if I had it going from both ends? So we have one form... So we on each step, we have... maybe we alternate steps, right? So we have our target molecule... so we work back... We work into the middle, right? So we start at the end, and we boil it down. And we start at the beginning, we build it up. And then as soon as they intersect, as soon as there's an overlap between those two sets, right? The ones that are boiling down and the ones that are building up, that's how we know we found a connection. And then we can return the number of, you know, opening steps. Okay, so that's... Oh, I wonder if we can do that. That would be very interesting. Okay, so what would I call that? So we have our target molecule, and we have our var. I'm going to create a new class within the molecule builder. I'm going to call it molecule boiler, I guess. I don't know. We're going to say class molecule boiler. Because that's the terminology I've been using. We're going to boil down from our target molecule and try to get back to E. And I am running out of time here. All right, I'm going to give us like 5 more minutes, and then I got to jump off. All right, molecule boiler var, target molecule, no, var, possible results. There's going to be a set string. You know, this would probably benefit from some multi-threading also. Anyway, possible results. It target. And this is going to be iteration, var iteration. Iteration. Int equals 0. Target molecule. It's a string. And possible results. No. Possible results equals set of target molecule. an iteration starts at 0, and we're going to do, oh, I also need rules. Rules. Okay, so the way this is going to work is we are going to take the possible results, func next step. We're going to do possible iteration plus equals 1. And then we're going to do possible results equals set possible results dot flat map molecule set string. And we're going to do let reactor equals reactor. Let reactor equals reactor. Start molecule. Oh, Jesus. We're at 129,000 possibilities. Okay. This is what the folding at home program was probably doing. This is why it takes so long. That thing that ran on PlayStation 4 with the little jiggling molecules. No, I guess it was PlayStation 3. Wow, that was a long time ago. The idea was that you could just leave your PlayStation 3 idle on, overnight or whatever, and it would, do what I imagine is something like this, where it's, computing possible molecules, for hours and hours and hours and hours, and that, computational power was then given to, some university or something like that to help cure cancer or something. I don't actually know what they were doing with it. All right. So then we need a function that does a reverse reaction. React. We're going to do func reverse react with rule. I'm just going to go ahead and copy all of this. Reverse react, and it's going to be output with input. Okay. And then we're going to do func reverse react with rules. And it's going to be basically this exact function, but instead of react, we're going to do reverse react. Reverse react. Okay. We're going to do let next results equals reactor dot reverse react with rules. Oh, yep, I forgot to var rules rule self dot rules equals rules. Okay. Going on? Why did I get a compiler error? Oh, because I already have that function. Oops. Completely forgot about that. I cannot. Okay. All right, so now in our run, we're going to do next step, and then we're going to do if is completed, then we'll break. Otherwise, we're going to we need our reverse reactor, var boiler equals, this has got to go up here, var boiler equals molecule boiler, self dot boiler equals molecule boiler, target molecule, target, rules. Okay, and then we're going to say is completed. So possible contains so possible outcomes dot intersection of boiler dot possible results dot count is greater than 0. Yeah, if the intersection is greater than 0, then we return. And our cumulative iteration is going to be return iteration plus boiler dot iteration. Right? And so this is going to be cumulative iteration. And then let's see if we can test it with, see if our test cases continue to pass. Fatal error. What? Oh, I forgot to give this a type. Okay, I can't tell if it's going faster or not. My test case is passed in roughly the same amount of time, but at that scale, that's not surprising. Let's see how quickly I get to step 7. Oops. I might have to call it. This is a tough one. Okay, so we're at step 7. I don't know how quickly that took. Feels like it didn't. Now wait a second. I might actually complete in half the... No, wait a second. Oh, damn it. I didn't actually iterate the boiler. Self.boiler. Next step. Boiler dot possible results. This actually seems slower. Seems remarkably slower. That is surprising. That is very surprising. All right, well, I don't know what I'm going to do here. I think I'm just going to let this run because I think we'll probably eventually get to the outcome, but that might take hours for all I know. Maybe I need to tune my reactor. Maybe that's something about my reactors running. It's inefficient. Maybe that'll be my next approach. All right, but I got to go. My day job awaits. So, all right. Thanks for sticking with me, everyone. See you tomorrow.